Hello everyone, my name is Rohit Singhal and we were discussing about the isomerism in alkenes. In the previous class, I have discussed about the structural isomers in alkenes, where I have discussed about chain isomerism and position isomerism. Now, in this class, we will discuss the another type of isomerism that is possible in the alkenes, that is geometrical isomerism. So, let us start with the topic. Geometrical isomerism, what it is, how it is different from the structural isomerism, that we will discuss. Okay. So, what is geometrical isomerism? Isomerism is still there, that means molecular formulas it's still gonna be same. Molecular formula will still be same. What will be the difference? The structures will different. Structure difference will be there, and how the structure will be different, how the structure will be different from the normal structural isomerism, that we will discuss in this class. Okay. So, the geometrical isomers, this is not found in alkenes. Alkenes there is no geometrical isomer, alkenes there is geometrical isomerism. Okay. I'll discuss this definition later onwards. First let's discuss what is it is through a few examples. Then we will discuss what what the definition is, how we can remember this. So, let's start with an example to better understand this. Okay. In the previous class, we have discussed about the C4H8 isomerism, in which we have written two isomers. One is CH2 double bond CH, CH2 CH3, right. Another one we write CH3 CH double bond CH CH3. So, let's take this for example right now. This was but 2 in. Okay. So, let's take this. If we have to draw the structure of it. Okay, draw the structure. So, what it will be? There is a C double bond C starting from the middle one. Okay. The two valencies are there. These two carbon I have drawn here. So, what we have now? There is one hydrogen and one CH3 group. There is one hydrogen and one CH3 group attached to both of the carbons. So, now it is a task that where to put in the hydrogen group and where to put the methyl group. You must be wondering that how that is going to create the difference between the two, but it will be. Let us see how. For example, I say I put an hydrogen here and there is another CH3. Let us put an hydrogen here and the CH3. Okay. What other possibility is there? There is one other possibility. C double bond C is right. Okay. So, now what will be? Is there an hydrogen CH3? Okay. Now, what we are saying that hydrogen is opposite to a CH3 group. Hydrogen is opposite to a CH3 group. Is there anything that hydrogen is opposite to the hydrogen? Okay, these structures. Now, the thing is, are these two structures same or different? This is the question, are these two structures same and different? Let us discuss this, let us try to solve this question. Okay. What we know what the double bond is. Okay. Double bond we know is a combination of a sigma bond and a pi bond. Okay. Double bond, what is in double bond? One sigma bond, one pi bond. Sigma bond is head to head overlap. What is pi bond? Sideways overlap. Okay. How it forms I have already discussed in the previous class also, but let us discuss here also. okay, this, and the other two valencies are there as it is. Okay, so this is a pi bond. So what happens in an alkene, that there's two structures that creates another kind of isomerism, that is geometrical isomerism, is due to the presence of this double bond. What happens when there is a head to head overlap, the bond can freely rotate on itself. When there is a pi bond, this is sideways overlap, so the restriction over this bond is restricted. So what happens, that the pi bonds are rigid, you can't freely rotate them. Rotation around the bond or C double bond C is restricted, you can't rotate it, and if you can't rotate it, this gives rise to another isomerism. This gives rise to what is called geometrical isomerism. Geometrical isomerism. So what two structures we have drawn? H CH3 H CH3, another one was C double bond C H H CH3 H3C. Okay, so what happens is, here if the bond rotation around the C double bond C is restricted, that means the position of hydrogen and CH3 is not exchangeable here. This is not exchangeable, and if these are two not exchangeable, then what happens is these two are different structures. And how we name it? There are two structures, and the name of the two structures will also be different. Now the molecular formula is same, yeah, it is same, but the structures are different. If the structures are different, the name will be different. How the name will be different? Okay, let's see. Just look after the which about the two same groups. Look the positions, or better to say arrangement of two same groups. For example, in this case we have hydrogens and we have methyl. Okay, so in the first case, let's take about the two hydrogens. So two hydrogens, what are two hydrogens? They are at same side, same with the methyl groups. What happens in this other case? Opposite side, opposite side, same group present on opposite side, and if these are present on the same side, this is known as cis isomers. What it is called? Cis isomer. If these are in the opposite side, it will be known as trans isomer. Okay. So this means what we have discussed, the two structures. Yes, the two structures are different. Why these two structures are different? Because the restricted rotation over the pi bond or the C double bond C, due to which the two substituents attached are not exchangeable, and we get two different isomers, in which first one is the two same groups are present on the same side. If they are on the same side, it is called cis isomer. If they are present on the opposite side, it will be known as trans isomer. And as I have discussed already, if there are two isomers, it will lead to a difference in physical and chemical properties. Okay, difference in physical or chemical properties. Here also both these two structures have different physical and chemical properties. this is a cis one, this one was the trans one. So let's talk about the physical properties. Chemical properties we will deal with later. What's the boiling point? Its boiling point is around 270 Kelvin, whereas the boiling point of the trans isomer is around 270. Okay, it's around 280, I think. Yeah, it's around 280 Kelvin. It will be around 275 Kelvin something. The row that I have given. So the dipole moment is different. Dipole moment. The dipole moment is not zero here, has some value. It has some value. While there is a dipole moment here, dipole moment is 0 in this case. How it's 0? Because what happens, the dipole moment, whatever the dipole moment is getting from this direction will be cancelled out by this direction, by this one. The dipole moment will be cancelled out. So the overall dipole moment is 0 in the trans isomers. So trans isomers are non-polar. It doesn't have any polarity. This dipole moment is 0. Dipole moment is 0. Okay. So now you must be wondering, however, I have told in isomers what isomers are. I have told you guys isomers are the same molecular formula but different structure. These two are different structures. But you must be wondering how the different between from the structural isomers or the geometrical isomers, how they are different. Because the hydrogen CH3 and hydrogen and CH3 both are attached to the same carbon before also in both the structures. So how these two structures are different and how we can distinguish between the structural isomers and geometrical isomers. So what we have seen in structural isomers, is the connectivity was different. The carbon to carbon connectivity was different. For example, these two is one thing. Okay, let's see. This one will satisfy the other one by the hydrogens. Okay, I'm just telling you what's the difference between that, and one is here. Okay, let's write CH3 also. This will be CH2, CH2, CH3. Okay, it will be CH3, CH, CH3, CH3. What we did in structural isomers, we have changed the connectivity of the carbon and carbon. For example, in this first case, what we have done, this is a 1 degree carbon. I have discussed na what is 1 degree carbon, what are 2 degree, 3 degree. This carbon attached only to one carbon, so 1 degree. This carbon attached to 2 carbons, 2 degree, 2 carbon, 2 degree, 2 carbon, 2 degree. What's this? 1 degree. What's this? 1 degree. This one attached to only one carbon, 1 degree, and this one is 3 degree attached to 3 carbons. So what we have done in structural isomers, we have changed the bond to bond connectivity. So the bond to bond connectivity will also lead to the difference in the primary carbons, the number of primary carbons or the secondary carbons or the tertiary carbons in the given molecular or the given structure or molecular formula, the structure what we can say. But what we in the structural isomers, you are saying in structural isomers, both of the carbons have same thing, structural isomers. We haven't done any such thing. In structural isomers, we haven't changed the bond to bond connectivity. Geometrical isomerism, sorry. In geometrical isomerism, we haven't changed the bond to bond connectivity. In structural isomers, bond to bond connectivity is different. Bond to bond connectivity or CC connectivity is same. What's different? The position, so the arrangement of the groups with respect to another groups is different. So, what is the difference in this? We have seen geometrical isomerism, the bond to bond connectivity is same, yes it is same, but we have changed the arrangement of the groups with respect to another group. How it is? We have kept this hydrogen here, and in one case we have kept one hydrogen on the same side of the another hydrogen, in the other one we have kept another hydrogen to the trans of that. So, we have changed the arrangement of the two groups. For example, let us say ki the two friends are standing close to each other and two friends are standing diagonally to each other. See, this is the two difference we have created. They have connected, so the same bond connectivity is there, but we have changed the arrangement, the spatial position, the position in the space we have changed. Okay, so this constitutes the geometrical isomerism, and such isomerisms, such isomers where the arrangement of groups are different, such isomers where isomerism that leads by the difference in arrangement or position, or by difference in the arrangement or position in space of the substrate attached are known as, what they are known as, stereoisomers. Okay. Isomers, you know, same molecular formula but different structure. Stereo means position in space. Okay. Space means a 3D space. Okay. So, these are called the stereoisomers. Okay. So, in this class we have discussed about these things, what we have started from the geometrical isomerism. In this class we have discussed how these are different from the structural isomers. We have taken an example of C4H8 previously discussed in the previous class. We have taken example of but2ene, where we have drawn the two possible structures. Then we think that whether these two structures are same or different, as the bond to bond connectivity is same, means hydrogen and CH3 are present in the same group in both the cases. But what is different in the case? The position in the space, the position of the methyl group and the position of hydrogens are different with respect to the position of another hydrogen and CH3 group that is attached to the second carbon. So, in that case, when there is an isomerism leading due to the difference in position of the substrate attached in the space, then it leads to the formation of the stereoisomers. Okay. So, how it is different? Structural isomers, there is a bond to bond connectivity is different, means the C bond C is different. It will also lead to the formation of different number of primary carbons or secondary carbons, that will change. So, C to C connectivity is different, whereas there is no such case in this structural geometrical isomerism. The C to C connectivity is same, but the difference is the position of the substrates attached in the space with respect to each other. Two kind of geometrical isomerism can be possible: stereoisomers in alkene. These two will be cis isomer and trans isomer. What is cis isomer? Cis isomers mean the two same groups are present on the same side. What is trans isomer? Two same groups are present on the opposite direction. Trans isomerism, obviously we have discussed the isomers that will lead to the difference in physical or chemical properties. Boiling points are different, melting points are different. Okay. It will also have the dipole moment different. How the dipole moment will be different? In cis isomerism there will be some dipole moment. However, in case of trans isomerism, whatever we are getting the dipole moment from one side will be cancelled out by the other side, because it is completely opposite to each other. So, that is why the trans isomers are non-polar. That means, the dipole moment of trans isomers is 0. So, in this class we have discussed this. In the from the next class onwards, we will discuss about the isomerism in alkynes, and we will also discuss how to a bit of nomenclature of the cis and trans isomers also. How to incorporate these cis and trans words in a structure, once in a name. We also have to see that. So, we will see that in the next class. Okay. Thank you so much.